the even and odd situation for the identities, and then we look at an identity that stands out really pretty cool, you know. These two identities look very, very similar, and the exercise that you will find below, it's going to give us another pretty interesting relation or difference between the two. So you'll see. Okay, so we need to prove the identity cosh squared minus sinh squared equals to 1. So as usual, we prove identities from left to right unless otherwise stated, you know, like show it on both ways, on both sides. So, well, so in order to prove this identity, we need to rewrite these hyperbolic functions in terms of their exponential definition. So recall that the cosh function, that's e to the x, e to the negative x over 2, and then minus e to the x, e to the negative x over 2 on quantity squared because of the powers of the hyperbolic functions. And while both identities look the same except the sign, cosh has a plus in the middle and sinh has a minus in the middle. Right? That's how we distinguish cosh from sinh. All right, so let's see. So let's start simplifying this madness here. Well, and I know it looks a little bit complicated, but trust me, this will simplify really, really nicely. Okay, so instead of splitting the fraction into the x over 2 and into the negative x over 2, which I think that's going to make things a lot more complicated. So what I'm going to do is use the quotient rule for powers. That is to write e to the x plus e to the negative x squared over 2 squared, which is going to give us a 4. And then minus e to the x minus e to the negative x quantity squared over 4 as well. And then now that we have everything in two fractions, notice these two fractions have the same denominator, so we can put everything together into a single fraction. So e to the x plus e to the negative x quantity squared minus e to the x minus e to the negative x squared, the whole thing over 4. This will be a lot helpful because we will do all the work in the numerator, and in the end, well, you'll see how this will reduce. Okay, so what do we have here? We need to square binomials. There's a couple of ways to square binomials. Okay, so one of them, when you have a plus b, for example, a plus b squared, typically if we write this as a product of the quantity and itself, right? And then we FOIL. Isn't it like the most common practice when it comes to this? Well, that's fine, but I think that's going to be a little time consuming, especially when writing the whole thing and then combining the like terms. So I'm going to take an alternative into this, and I'm going to go through this way pretty much the entire semester because we will be using this a lot within problems or types of exercise that require even longer time than this. So I do this in order to save us some time. So when you have a plus or minus b quantity squared, well, we call this a special product or binomial squared. So there's a couple of ways to describe. It's the square root of the first term plus or minus, depending on the case, whether we have a plus or whether we have a minus, 2 times the product of the first term and the second term plus the second term squared. So that's going to save a lot of time, trust me. But of course, I mean, when you're doing the homework or on the exam, if you feel more comfortable doing it the FOIL way, of course that's valid, that's acceptable, you know, as long as you get the same result, right? So that shouldn't be an issue. Okay. Well, so let's use this idea to square these two binomials. So on the one hand, so we need to square e to the x quantity squared. Is that going to give me e to the x squared? When I square e to the x, what is that going to give us then? e to the 2x, all right? That's e to the 2x. Be careful, that's a very, very common mistake you want to be aware of. So e to the 2x plus, in this case because of the positive, 2 times the product of the two terms, e to the x, e to the negative x, plus e to the negative 2x. So we multiply this 2 with the power negative x. And okay, not yet, minus parentheses, the same quantity, the same process, e to the 2x, minus, in this case, because we have a negative sign in between, 2 times e to the 2, or e to the x, e to the negative x, plus e to the negative 2x. And the whole thing divided by 4. Okay? Alright, I know it looks like we're expanding the problem. It looks like we're making it harder than it, or more complicated than it initially was. But trust me, this is going to simplify really, really nicely. So check this out. Number one, we can start by canceling this e to the x with e to the negative x. How come? Well, because e to the x times e to the negative x, this is the same as saying e to the x, and write the exponential that contains the negative power in the denominator. That reduces to 1. Okay? So in this case we will end up with the following: e to the 2x plus 2 plus e to the negative 2x. And okay, in this case I'm going to distribute the negative over all the terms right here. So negative e to the 2x, negative times negative is positive, plus 2, and negative times positive is also negative e to the negative 2x, the whole thing over 4. And we will further cancel terms out. Alright? So let's cancel this e to the x with e to the with negative e to the x. They're like terms, they're just opposite in sign. We can also cancel out this e to the negative 2x with e to the negative 2x. Right? And what else can we do here? Well, the only terms that survive the simplification in here are the 2's here. So we would end up with 2 plus 2, which equals to 4. Divided by 4, what's that equal to? Isn't that what we wanted to show from the identity? Okay, so yeah, that's, the usual process of proving an identity. Nothing weird, you know. But well, I was mentioning before that this identity, it's another pretty cool connection and distinction between hyperbolic function and trigonometric function. Okay, so let's go back to the picture from day one. Okay, again, this all stems from the fact that trigonometric functions are functions that describe points around the circle. Well, for the sake of simplicity, we just talk about the unit circle, but ultimately can be a circle of any radii. So that's not limited to just a unit circle. As opposed to hyperbolic functions are functions that describe points along the hyperbola. All right. So, again, just to be clear here, this is x and this is y. X and y. All right. If we use this idea, okay, let me go back to cosine squared theta plus sine squared theta equals to 1. But recall that cosine is the x-coordinate of the points on the circle, so that's x squared, and sine is the y-coordinate, which is going to give us a y squared equals to 1. What's that equation, by the way? Does that remind you of anything? Pythagorean theorem? Well, yes. It's a circle of radius 1. Surprise, right? Those are the points that describe the unit circle in terms of sine and cosine. Although we're going to look at this phenomena more in depth at the end of the semester when we describe parametric equations.
So does that mean if, for example, something like this was asked on the S and we substituted it with X and Y and got this answer, is that okay?
Yeah, but no, we're not going to do this on the test because with this I'm just going a little bit ahead of the game for towards the end of the semester in terms of what parametric equations will describe this. Now for the test, what you would be asked is to compute some limits, derivatives involving hyperbolic. Now with this identity here, Cauchy square, okay, let me use theta even though we don't use theta here. Minus sinh squared. Theta equals to 1. Again, if we go with the same idea that Cauchy describes the x-coordinate of those points that go along the hyperbola, well, this is x squared minus sinh, which describes the y-coordinate. Does that equation remind you of anything? It's a hyperbola. That's the whole thing about it, you know? Trigonometric functions, circular functions, hyperbolic functions, hyperbola. So I think this is a pretty cool relation between the two. I mean, how they put together, how they're different and how they're related, right? So, but of course, again, we're going to look at this. What I was doing is basically changing the parameter, which is something you're not responsible to know for now. That's something that we will go in depth at the end of the semester in chapter 10. So don't worry. Okay, so let's moving on through hyperbolic functions. Well, we already did the definition, where they come from, derivation of some of them, worked with some numerical values involving them, and well, so let's keep moving on. So now let's do let's jump to the calculus of hyperbolic functions. And as well, if you recall from the last semester in Calc 1, well, calculus basically starts with limits. So let's compute a limit involving hyperbolic functions. But I mean, even though these limits look very I don't know, very innocent, if you will. I mean, tanh of 2 times infinity, that's a tanh of infinity, because 2 times infinity, it's still a bigger infinity. Well, what's this? We have no idea of what tanh of infinity is. And unfortunately, in this case, we will have to go through the definitions in terms of exponential functions. So, because even if you use a graphing calculator to compute this, most calculators may not contain a built-in function to compute hyperbolics, or maybe some of them. But still, of course, on the exam, the calculators are not allowed. The idea is that we are familiar with the definitions of these hyperbolic functions in terms of exponentials. And from last time, you might remember that tanh x equals e to the x minus e to the negative x over e to the x plus e to the negative x. That's and that came from dividing sinh over Cauchy, which is one of the similarities between hyperbolics and trigonometrics. But in this case, well, this is just for x. For the limit that we have in here, we have a 2x. So all we do is change this x with a 2x. So that's the limit e to the 2x minus e to the negative x, negative 2x rather, e to the 2x plus e to the negative 2x. X approaches infinity. All right? So let's see. Well, let's see what about this limit? Okay, if we analyze every single part or portion of the limit, well, ultimately we want to look at the behavior at infinity, right? So where is this term going to go as x goes to infinity?
0.
What about this one?
0.
All right. What about the other two? Infinity, right? Well, so we basically have the infinity over infinity indeterminate form, right? Well, that's good because that tells us that we can use any algebraic manipulation possible to write this limit in a convenient way that we can compute this limit. Okay, let's go back, let's go even further back to pre-calculus and calculus 1 together. Okay. When it came to finding limits, okay, let's see. Let me just make something up here, something like limit 3x cubed plus 4x squared plus 1 over 7x cubed plus 4x squared plus 1 as x approaches infinity. Up to this point in Calc 2, it's fine if you use the shortcut rules for a limit and infinity. And well, and does anybody have an idea of what this limit is? 3 over 7. How come?
Because of degrees. Well, you have to divide by x to the third for all of them.
Well, yes, I'm glad you brought that up. So number 1, from the shortcut rules, let me mention those 3 shortcut rules. Number 1, and whenever you have polynomial over polynomial and the degrees match, like in this case, all you have to do is go with the ratio of the limit of the leading coefficient. So that's fine. Rule number 2, when the degree of the denominator is, okay, let me change this to 4, for example. When the degree in the denominator is larger than the degree on the numerator, the limit here is 0, because you have a larger quantity in the denominator, and well, recall that when you divide by a really big number, you get smaller number. How small? Basically to nothing, which is 0. You know, I use this analogy of, for example, when you share a pizza, for example, if you share with a friend, well, you get half of it. Share with 9 friends, you get 1/10 of the pizza. You share with a million people, you get every time you get less. Share with infinitely many people, you get nothing, right? So that's the analogy I like using. Okay, the other case, when the degree in the numerator is larger than the degree in the denominator, well, we have a larger quantity in the numerator than in the denominator, so the limit should be infinity. So this limit blows up to infinity. All right, so, but this is with polynomials. So ultimately, and like mentioned before, the long process, the painful process that they made you do in Calculus 1 was to divide. Okay, let me go back to the older. Is to divide by the highest power of x that you see in the limit. All right. Yeah, it was quite a setup. It was quite a painful setup. Ultimately, just to cancel this, and 2 over 4, that reduces, that goes to 0, that goes to 0, that goes to 0, that goes to 0, and we still end up with 3/7, as if we use only the shortcut rules of going with the degree matching. So guys, at this point, I believe it's fine if you just go with that. Don't need to show this painful process. However, I will have to show a slightly painful process in here for this limit. But I mean, how do we relate this limit with the exponential? Because in this case we have polynomial over polynomial, and for polynomials we talk about their degrees, right? That's what we're taking into account to determine which shortcut rule to use. These are not polynomials. Well, they will be later. Don't want to spoil too much from power series, but you'll see how these are actually polynomial. That'll be later. Now, in this case, they're not polynomials for now, but still, one between the two exponentials, the e to the 2x and the e to the negative 2x, one of them is higher in order than the other one, right? Which one is higher in order? Is the e to the 2x or the e to the negative 2x? e to the 2x, because that, for any value of x at infinity, that's going to produce larger numbers, not the other one. And well, in this case, well, I'm going to divide every exponential term right here by, well, in this case, not the highest, not by x of the highest power like we did in the polynomials. In this case, by the exponential of the highest order, in this case, the e to the x, okay? So that's the limit, e to the 2x minus e to the negative 2x over e to the 2x over e to the 2x, the whole thing over e to the 2x plus e to the 2x, not rather negative, and e to the 2x, e to the 2x, and as x approaches infinity. Okay? Well, number one, we can cancel out these to 1. We can cancel out these to 1. But be careful with the other two. That's going to be the limit of 1 minus, okay, what will be e to the negative 2x divided by e to the 2x? Number one, what do we do with exponents when we have the quotient with the same base? Subtract. So what is negative 2x minus 2x? Negative 4x. Be very careful with signs in here. So e to the negative 4x, and same in the denominator, but with positive sign as x approaches infinity. All right? And well, so let's see. So it looks like we have an even more friendly expression to work with. Well, so where is this term going to go as x approaches infinity ultimately? 0. What about this one? 0, right? 1 minus 0, 1 plus 0, that's going to be 1 over 1, which is 1. So the limit is 1. All right? So we would, maybe it's an expected result, you know, because you have like a tanh function. It's a function that relies on hyperbole, that relies on exponentials, and exponentials get big, right? So you would have thought that this limit would have been infinity, but recall that these hyperbolics not only have exponentials with positive that grow, they also rely on exponentials that decay. So there's a combination here. So that's why we have to do all this setup for this limit. All right. Questions about this? Yes.
So if we have the top, which is e to the 2x minus e to the negative 2x, and then on the bottom we have the exact same thing, why can't we just call that 1 since it's the exact same thing? Oh, never mind.
Or because of the signs, right? So I mean, another way to visualize this limit, okay, and I didn't want to do this using a shortcut way. I mean, there's still a shortcut way for this limit, and because we have higher order, they're both the same order. The order is 2x, right? The power is 2x. But in this case, we have an invisible coefficient of 1. The remaining terms which are lower in order are pretty much negligible, because really the terms that contribute to the value of the limit are the leading terms in this case, right? And yes, 1 over 1, well, it's still 1, but at least for this kind of limit, you're expected to show some process in here. You had another question in the back?
So if you can prove that the original function is indeterminate, can you do L'Hopital's rule?
That's another alternative, L'Hopital's rule. Yes, we could have done L'Hopital's rule. However, okay, yes, okay. Let me show you this. So if we do the L'Hopital's rule, limit x approaches infinity, that'll be 2e to the 2x minus, or rather plus 2e to the negative 2x, the whole thing over, what is this? 2e to the 2x minus e to the negative 2x. All right? So, do you see how the expression pretty much looks like the same? And in fact, what we're doing is even making it even more complicated by adding these multiple factors. And the idea of the L'Hopital's rule is to have that numerator and denominator a little bit simplified every time we do the L'Hopital's rule. Well, in some cases, those limits computed via the L'Hopital's rule can give us a final answer by only one iteration of the L'Hopital's rule. In some cases, repeated L'Hopital's rule is required, but in this case, it doesn't seem like it's going to help, because if we do it again, okay, 2 times 2, 4e to the 2x, you see how these numbers just become bigger and bigger, so I don't think it's working. Question? One half, exactly. It will be 1/2. Yeah. Alright, so now that we looked at one limit exercise, so let's keep moving on through the calculus. Well, what was next to limits in Calc 1? Of course, derivative. So when we needed the derivative, the construction of the derivative, in order to construct the concept of the concept of the limit, to construct the concept of the derivative, because of the approximations, the limits, making that distance between the 2 points in the secant to be as close as possible, in order to make this a tangent, you know the whole story about it. All right, and well, so here we have the formulas to differentiate hyperbolic functions, and again, there will be similarities and differences between the derivatives of trigonometric functions and the derivatives of hyperbolic functions. Okay, so how about we recall the derivatives of trigonometric functions? I'm gonna go sine x prime. What's the derivative of sine? Cosine. What's the derivative of cosine? Negative sine. The derivative of tangent? Secant squared. The derivative of cotangent? Negative cosecant. The derivative of secant? Secant tangent, correct. And the derivative of cosecant? Okay, so those were the derivatives of the trigonometric functions from Calculus 1. Well, of course, we might use this. It's good to review them, because we're going to use them when we get into finding integration and all those methods of integration that will come later. Will come soon, rather. Okay, so let's observe these formulas. Let's compare them with the hyperbolic ones. So as you can tell, well, the derivative of sine is cosine. The derivative of sinh is cos. The derivative of cosine is sine. The derivative of cos involves a sinh as well. So they are the same entity in this case in terms of what their derivatives are. However, the difference here is that when listing the trigonometric functions in this order, we have the derivative of the first one to be a positive, the next one is negative, positive, negative. See how they alternate in signs? Okay, so that's not true in the hyperbolic world. In the hyperbolics, it is the first three, sinh, cos, and tang, for which their derivatives are positive, and the remaining three, it looks like I forgot, no, negative, never mind. The remaining three are negative, so the signs do not alternate as opposed to the trigonometric functions. So it's the first three are positive, the remaining three are negative. All right, so that's a distinction that it's important to take into consideration. Again, similarities and differences between the two. All right. And of course, how about we see this function, these derivatives in action? So let's find the derivative of this function right here, the derivative of e to the 3x cos 5x cubed. Okay, before jumping into the work here, let's have a look and review the different differentiation rules and find out which rules are going to be involved, because there's going to be more than one rule, all right? So, any ideas?
My guess is chain rule and product rule.
Chain rule and product rule, do we all agree? Chain rule with product rule? Of course, because well, we have a product of the function, and each individual function are both composition functions, and to differentiate composition functions we use the chain rule. So number one, I think it would be a good idea to recall what the product rule is. So the derivative of product u times v prime, that's u prime v plus v prime u. Okay, to demystify this, well, this is the derivative of the first factor in the function, the derivative of the first function times the second function without differentiate, plus the derivative of the second function times only the first one without differentiate. That's what the product rule is. Let's see it in action in combination with chain rule and the new rules to differentiate hyperbolics. All right, so let's call this, it's important, notation is important, f prime. That's to denote that this is the derivative. And well, so e to the derivative of the first factor of the u is, well, for the exponential is itself times by the chain rule, the derivative of the quantity that we have in the exponent, the derivative of 3x to the second, that's a 6x. That times cos 5x cubed. Okay, what do we have for now? What do we have so far? This comprises the u prime, this comprises the v. So that's the u prime v part. Okay, let's do the next part. For the next part, okay, that's the v prime. In this case, the v is the hyperbolic, the derivative of cos. Be careful, it's not negative cos like in trigonometry. In trigonometry, it was negative sign, not in hyperbolics. Sinh 5x cubed, but because this is a composite function, we need to multiply by the derivative of 5x cubed, which happens to be 15x squared. Okay? And then from here, well, that's times u, which is e to the 3x squared. What's this ultimately? Well, this part comprises the v prime, and this part comprises the u. So that's the product rule in action. Everything labeled, just so nothing is mysterious at all. U prime v plus v prime u. Okay, there's really not that much to simplify or combine, other than maybe factoring the greatest common factor. Alright, so looking at this result, it seems like the common factor is the e to the 3x squared. And not only that, so let's see if we have anything else. Okay, let's look at the numbers. Between 6 and 15, they both have a common factor. I believe it's a 3. And between x and x squared, we can factor out 1 power of x. That's going to leave us with 2 cos 5x cubed plus 3 times what equals 15? Is that a 5? And because I factored out 1 power of x, I'm left with 1 power of x out of the 2. And that's a sinh 5x cubed. And we can call this our final answer. Okay? There's really not that much to really simplify, more like factoring GCFs, right? Letter B, cosh of ln x, another composition function. Any ideas on which differentiation rules might be used? Well, here. Chain rule, what else? The derivative of log of ln, and what else? One more? Cosh, all right? So 3 rules in the same one. Well, y prime, the derivative of cosh, again, sinh ln x, right? There's really nothing crazy, times the derivative of ln x, which is, and there's really nothing else to do. That's all. I mean, of course, we could make up a lot of functions to differentiate, combine all the rules. I mean, here in this case we use product rule, chain rule. You may have situations with quotient rule as well, or hyperbolics inside the radicals, etc. Okay, so let's see what's next. Well, of course, I mean, so when we talk about hyperbolic functions, which we already learned that these are functions that are described in terms of exponential functions, we know that exponential functions have an inverse, right? What's the inverse of the exponential function? The logarithmic function. So we are going to use the same idea from there in order to describe these functions. I mean, the fact that we have, this is, you know, the definition of going back and forth between a function and its inverse, right? So, and the reason I mentioned that these exponential functions have as their inverses the logarithmic functions, it's because that shouldn't be a surprise that inverse hyperbolic functions should be described or represented in terms of the inverse functions of those exponential functions, right? So, which is logarithmic functions, right? So, this again, it shouldn't be really surprising. Although deriving these functions might take a long time. So, and also I don't think you will be responsible to memorize these inverse ones, because, well, actually this type of inverse hyperbolic functions will come later in your mathematical career and in your engineering career, especially for those of you that are electrical engineers. So somewhere along the way you will run into complex analysis and Fourier analysis and analysis of signals and circuits, and a lot of these type of problems are modeled in terms of, well, number one, functions of complex variables that also put together hyperbolics and inverse hyperbolic functions. Well, I don't want to really get into this, like it's too early to do that, but you will see that later. The idea is just for now is that you see that this exists, so when you get to those courses, in your later courses, when you get to your later courses, you go like, oh yes, it was mentioned at least in Calc 2, okay? But of course, at least we're going to do the derivatives of inverse trigonometric functions. Well, and again, not too surprisingly, there's differences and there's some similarities between the derivatives of inverse trigonometric functions and inverse hyperbolic functions. To begin with, okay, so what's the derivative of sine inverse of x? Does anybody remember that formula? One over the square root of x. 1 minus x squared, right? 1 minus x squared. Okay, do you see a similarity with the hyperbolic counterpart? It's the sign only, right? That's the main difference here. So, okay. And of course, the remaining ones have very similar, I mean, phenomenon here, you know, in terms of how do we relate them? So let's just use this new formula. So how about we differentiate cosh inverse of x cubed? Well, in this case, let's use this formula. G of x, G prime of x, not g of x, careful. That's the square root of, well, in this case, the derivative of cosh inverse is given only for x, but in this case, because we have a composite function, we should replace the x with what we have in as a composite part. In this case, well, we need to square whatever that part is, in this case, x cubed minus 1. But be careful here. That should be, because this is a composition function that involves a chain rule, so we need to differentiate the x cubed whose derivative is 3x squared. All right? Well, let's simplify. Yes?
Why is it minus 1?
Oh, this one? It's the inverse cosh.
I'm sorry, you're right.
No worries. No, I'm glad you asked. Okay, feel free to ask at any time. Feel free to stop. Okay. So yes.
So can I write it as sine h?
Yeah, I think that notation is valid. Okay, cosh inverse x. It's also arc cosh. Yep, that's the other notation. That's fine.
Isn't that 1 minus x squared?
One. Which one?
I read the proposed inverse cosh.
Mm-hmm.
1 minus radical 1.
Oh, okay. No, it's x squared minus 1. It's the second formula here. Yeah. No worries. Well, so we still need to simplify this expression. We're pretty much done with the calculus. So let's see. X cubed to the second power. What do we do with the power? Do we add 3 plus 2? Multiply. Power of another power, multiply the powers. That's, 3x squared over the square root of x to the 6 minus 1. And let's call it for this exercise. Okay, I'm going to need more space in here. Okay. Letter B. Oh, what about letter B? It looks a little funky. It has a product. It has a tangent. Also has an ln with a radical. Looks like one of those problems that are going to take forever. But trust me, this problem will simplify really, really nicely. Well, so here is the thing. Okay, so we have a product. Let's use the product rule. Y prime equals the derivative of x, which is 1. I'm going to write that 1 so you can see where is that, or so you can see how am I using the product rule. That times tangent plus the derivative of tangent inverse, which in this case is this formula right here, 1 over 1 minus x squared, and times x, which is the u prime v plus v prime u. Okay, that's the product rule in action with the first term. However, okay, don't write this. Don't write it. Let me show you what happens here. The derivative of the natural log function, it's always 1 over whatever it's inside the radical. All right? I mean, 1 over the quantity inside the natural log function, which is in this case the radical, and then that times the derivative of this radical, right? But do you see the issues with having to do another chain rule with radicals? That's going to take for sure some 3 or 4 more steps. So what do we do about it? Well, I'm going to go back to the original function and rewrite x tangent inverse of x plus ln of 1 minus x squared to the 1/2. All right, by properties of radicals, the denominator of the rational exponent is the index of the radical, right? And then From here, I'm going to use that property of logarithms that we talked about last time, the SmackDown basketball rule. Remember that rule? And I'm going to have this power to become a coefficient. Do not confuse with the power rule to differentiate. This is not that. Well, that's going to become x tanh inverse of x plus 1/2 ln of 1 minus x squared. And if you look at this second term, it will be a lot simpler to differentiate rather than having those crazy radicals that I had before. Alright? So the moral here is that in some cases it's suggested to do some algebra first to make something a lot more simpler, and so we can differentiate it a lot more easily. So this will be 1/2 times, okay, we can differentiate the log 1 over, instead of having the radical, 1 minus x squared times the derivative of this, which is negative 2x. So someone raise a hand over here. Okay. Well, so this will, number one, simplify the 2 with the 2. And yes, this derivative already looks very, very crazy with the number of terms, but trust me, see how this is going to simplify. So that's going to be 1 times tanh inverse, that's tanh inverse, plus x over 1 minus x squared, and then positive times a negative, that's a negative. I'm going to have this x in the numerator, 1 minus x squared, and do you see the magic here? Cancel. Final answer, tanh inverse of x. Right? Questions about it?